Hello and welcome to the Computing Conversations column. This column is from the September 2013 issue of IEEE Computer and is titled John C. Hollar, History of Computing. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I am the editor of the column, and I'm Charles Severance from the University of Michigan. For anyone visiting the San Francisco area, a visit to the Computer History Museum in Mountain View is an important stop. The Bay Area is home to Silicon Valley, the center of the universe for many of the past 30 years' worth of technological breakthroughs. It is difficult to see Silicon Valley as you drive around, but the Computer History Museum gives a unique opportunity to learn about the people and technologies that have an ever-increasing impact in our lives. The Computer History Museum focuses both on the technical artifacts that make up our computational past, as well as the human stories of the challenges, risks, and failures that led through the breakthroughs that define our field. One of the earliest artifacts in the museum is the Babbage difference engine that computes polynomials using mechanical computation.
I love the Babbage engine because it's such a model of the way I think great computing and great innovation works. Charles Babbage was a brilliant mathematician, and the problem that he was trying to solve, of course, was these books of log tables that were filled with typographical errors. All of the calculations had to be done by hand, they had to be transcribed by hand, they had to be typeset by hand. The margin for error in the publications of these books was phenomenal, and British armadas were finding themselves hundreds or thousands of miles off course because they were using these error-filled books to try to do the most basic calculations. Those things were happening throughout industrial Britain at the time as well. So Babbage dreamed of a special purpose, extremely sophisticated calculator that would take all the guesswork and the human intervention out of generating these tables, these answers. And it was exactly the right approach to exactly the right problem. The difficulty was that, like many entrepreneurs, Babbage had a brilliant idea but couldn't get it funded. And he never got further than building a piece of the engine, but he built the blueprints for the full engine in fantastic detail.
Although Babbage designed his difference engine in great detail, he never knew if it would actually work. In 1985, some 150 years after its conception, engineers and specialists at the London Science Museum undertook building a difference engine based on Babbage's original plans. They completed the first difference engine in 2002, and you can view it in London.
There is a second engine that was built. The first one is in London, the second one is here at the museum, and it is the complete Babbage engine because Babbage not only envisioned this enormously complicated 2-ton machine with 8,000 moving parts, but he envisioned a printer and he envisioned a stamper that would create the plate from which the book could be printed. So it was really the complete solution, and Babbage dreamed of warehouses full of these machines being driven by steam engines, so they'd be constantly calculating. And our machine, which we crank every day at 2 o'clock Pacific time, is now working exactly as Babbage envisioned. So that whole story is, I think, so special. It's a brilliant mind solving a difficult problem with an incredibly well-engineered solution, who yet, as brilliant as he was, couldn't get it funded, died embittered and wondering what the world might have been if he'd been able to create it. And a generation later, entrepreneurs, if you will, working on those plans and making it come to life. And so for audiences here at the museum to see the Babbage engine work and hear that story is a really very special thing.
In the 1930s and 1940s, computing moved from mechanical to electronic devices, triggered initially by technological breakthroughs, followed by rapid innovation, as well as problems and conflicts.
I love our recreation of the Atanasoff-Berry computer. First of all, it's the only one that exists. It was built exactly according to the plans that John Vincent Atanasoff and Clifford Berry devised at Iowa State in the 1930s. It, of course, was the subject of the very famous patent dispute that destroyed all of Eckert and Mauchly's original patents on the ENIAC and the birth of electronic computing. As Gordon Bell calls it, it was the disinvention of the computer. And it's also, I think, very interesting because Atanasoff himself is not well known in history. Neither are Eckert and Mauchly, neither is John von Neumann, Conrad Zuse, all these people who worked on the Manchester Baby and the Williams Kilburn tubes. Those are not well-known people, but you can stand in that gallery here, which is called The Birth of the Computer, and you can see the ABC computer in all of its simplicity, standing right next to the Johnniac, von Neumann's famous computer, and one of the first Williams Kilburn tubes, and the Enigma encoding machine, which was next to a film about code breaking in World War II. And so much of history comes together in the space of about 1,000 square feet with the real machine sitting there. And that whole gallery is special to me, but the Atanasoff Berry computer especially so because of Atanasoff in particular.
In our field, amazing breakthroughs in innovation are always followed by the scaling up in practical applications of the new technologies. By the 1960s, IBM was designing the 360 architecture that's still in wide use today.
Great story, not only because of the system, but because it was a bet the company decision by Tom Watson. He, in that period of the 1960s, spent what would today be the equivalent of about $60 billion in R&D money on a single project, which succeeded and charted IBM's course for the next half century, and if it had failed, would have sunk the company.
The electronic computing revolution went from vacuum tubes in the 1930s to transistors in the late 40s to the invention of the integrated circuit in the late 1950s. 60 years later, our current technology is still based on the increasingly powerful and sophisticated integrated circuits. The invention of integrated circuits both created and gave the name to Silicon Valley.
We've got a replica of Jack Kilby's notebook open to the page in September 1958, where he records for the first time his whole design for his version of the integrated circuit. Sitting there in Texas Instruments, is told by his bosses, in the middle of a Texas summer, don't work on this idea, Jack. We all know you're in love with it, but you've got another job. They all leave on vacation, and what does Kilby do but spend a month working on the integrated circuit? Comes back to his bosses in September, hooks it up to an oscilloscope, and it works exactly as he predicted. At the very same moment, out here at Fairchild, Noyce and Moore and Ernie and Last are working on the same idea, and within a period of months, literally the Big Bang in computing has happened, and everything changes.
Once we had the integrated circuit in hand, we quickly went from invention to engineering. The goal was to make cheaper and faster integrated circuits. Gordon E. Moore coined Moore's Law, which stated that the number of transistors we could put onto an integrated circuit would double about every 2 years. He predicted the trend in a paper in 1965, and it has been remarkably accurate even to the present day.
The semiconductor gallery, if you come to the museum, is a really special gallery. We have wonderful examples of wafers as small as a nickel and as large as bigger than a dinner plate. And you can see the evolution over time of how complicated it is to make a microprocessor and how difficult the science is.
As is always the case, once a scientific or engineering breakthrough happens, the real money is in applying these new technologies to solve human problems. The creation of increasingly powerful and inexpensive integrated circuitry unleashed a torrent of new applications for computing technologies.
You turn a corner and you go down what I call application alley, because in very quick succession you go to artificial intelligence and robotics, and graphics and music and art, and then Xerox PARC, the birth of the graphical interface, the mouse, the corded keyboard that Doug Engelbart invented, gaming, the first Pong machine, the birth of Atari, all the gaming companies that came after that, the personal computer, the Macintosh, IBM PC battles, a million different flavors of PCs that flourished out from under that, mobile computing, the internet, the World Wide Web, and then a theater called What's Next? So you go through this in very quick succession after you go through the integrated circuit, and you come to a world that we're experiencing in a very personal way now, but yet once you've walked through it, you know that somehow we're still only just at the beginning.
As we've moved from the era of mechanical computing to cell phones that are more powerful than the massive supercomputers of the past, it's important for all of us in computer science to understand what it took to create our current technologies so that we can best imagine how we might make our own contributions and continue to evolve our field. This column is from the September 2013 issue of IEEE Computer and is titled John C. Hollar, History of Computing. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I am the editor of the column, and I'm Charles Severance from the University of Michigan.